So, good evening, everyone. Welcome to the second live session for the course Concrete Technology offered by NPTEL. I am Arshit Agrawal, a PMRF PhD scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for this course for the entire duration of the course. So, in today's session, we'll first revisit the last live session, just a quick recap to whatever we saw last week, and then we'll look through the things covered in the week two content of the course. So, the week two content that we will discuss today is divided into four segments. First, we will discuss about the leftover part from week one content that is about different types of water in cement paste and porosity in cement paste assembly. Then moving into week 2 content, we will discuss about different testing methods for cement and different types of cement used for concreting. In between, I will have questions related to the content. So in total, there will be around 14 to 15 questions today, and after the session I will keep myself available to try and address any other queries post our regular discussion. I hope everyone are clear with the session's timeline, so I will start now. So last week we started with the course where we first had a basic introduction to concrete as a composite material made of binding material, water, aggregates, and admixture. Each of these components have their own specific role which contributes to the strength and the performance of concrete, for which we had a brief overview. Then we started with binding material discussion, where we first talked about lime, how lime is used as a binder, as a binding material, and we understood the lime cycle, and we talked about hydraulic and non-hydraulic lime. Then we came to Portland cement, where we first talked about the production of Portland cement clinker and different stages in the production process and different activities happening in the kiln phase at different temperature. We talked about oxide and compound composition of Portland cement and how using Bogue's relation, if we know the oxide composition, we can find the compound composition. Then we talked about microstructure, where we answered three questions. First, why certain cement phases are formed. We talked about silicates and a tetrahedra geometry, where the presence of unbalanced charges in the silicates leads to linkage and polymerization. Now, to balance these unbalanced charges, we discussed how C2S and C3S are formed. And similarly, we discussed about aluminates, which also has tetrahedra geometry, and it forms C3A. And since C3 has an open cubic structure, it is more reactive compared to C2S and C3S. Then we talked about why cement hydrate. So this is because of large anion and small cation arrangement, where to achieve a stable packing density, these compound they engulf water in their structure, and this reaction is known as hydration reaction. Then we talked about how cement hydrates. So we saw hydration of silicates, hydration of aluminates, and role of gypsum in hydration of aluminate. For silicates, we saw hydration of C3S, alite phase, and hydration of C2S, belite phase, and we saw what is the difference between the two in terms of how much calcium hydroxide they are producing. And then hydration of aluminates, where we talked about flesh setting that occurs initially due to high reactivity of C3A, and then why gypsum is added. When we add gypsum, it reacts with C3 to form ettringite, and this ettringite delays the flesh setting. However, if the gypsum is consumed and there is more C3 in the system, then ettringite converts into monosulfate, which can lead to problem of cracking later on, because as sulfate ion ingresses through concrete, it can react with monosulfate and convert it back to ettringite, which is an expansive reaction. So this we had a little overview of. Then we talked about two important properties of cement hydration: heat of hydration and degree of hydration. And we understood in terms of different stages how heat of hydration grows, and degree of hydration how water consumption and happens as the hydration grows. So now, since we have a basic idea of cement hydration, there are two more important entities which are associated with cement hydration. One is water, and another one is porosity. Okay, so first let's talk about different types of water in a cement hydration. So there is three main classification of water after cement, after hydration reaction happens. First is the capillary water, second is the gel water, and third is the chemically bound water. Okay, so what is capillary water? Capillary water is the free water that is present inside the pores of the cement paste. Okay, so if I talk about hydrated cement system, cement paste system, so whatever water is free inside this paste, cement paste system, these are known as capillary water. Okay, so in larger pores, this water upon evaporation they don't cause any kind of shrinkage problem. However, the water which are trapped in smaller pores, capillary water which are trapped in smaller pores, they are held by tension, capillary tension, which can cause some shrinkage upon drying. Okay, then there is gel water. So gel water is something which can be classified in two ways: adsorbed water and interlayer water. So absorbed water is the water that is present on the surface of hydration products. Okay, so I have CSH, layer structure of CSH. The water which is absorbed on the surface of CSH, this is known as adsorbed gel water. And the water which is present in between layers of CSH, this is known as interlayer water. Okay, so these water they don't dry off easily. Okay, and if they dry off, then it will bring a lot of shrinkage and even collapse of CSH structure. Okay, so capillary water was something which is free water between hydrated products, and gel water is something which is attached to hydrated product or engulfed between hydrated product. Okay, and then third category is chemically bound water. So chemically bound water is the water that is actually contributing in the hydration. So when we talk about CSH, this H, this is my chemically bound water which has all participated in the reaction. Okay, and it will be removed only on ignition to high temperatures. Okay, so there is one very famous explanation of different types of water in cement hydration using this Feldman-Serede model of CSH structure. So in this structure, you can see different types of water apart from this chemically bound water. So you see, this is my layered structure of CSH. Okay, the water that is absorbed over this layer, the blue circles. Okay, these are physically absorbed water. Okay, then and the water which are showed by these yellow crosses, these are interlayer water, so they both come in the category of gel water. And the water which will be present in between these hydration product in these free spaces, this water will be capillary water. Okay, so this is a very famous representation to understand different types of water in a cement based system. Now, if we specifically talk about chemically bound water, this water is important for us from hydration point of view. Why? Because it is the actual amount of water that is required by the cement to undergo complete hydration. Because this is the water which is contributing in hydration. Okay, so if we know the clinker composition and we know for each clinker phase how much water is required for hydration, we can say that the required water to cement ratio for complete hydration can be written by this equation. Okay, so W by C ratio is A1 times C3 is A2 times C2 is A3 times C3 and A4 times C4AF. So what is this A1, A2, A3, A4AF? These are the amount of water consumed by different compounds for complete hydration. So how much water C3S requires for complete hydration, how much water C2S requires for complete hydration, this is that factor. Okay, A1, A2, A3, A4. Okay, now there have been long term studies that have been done to find the value of A1, A2, A3, A4, and people have come across these values, like A1 is equal to 0.23, A2 is equal to 0.96, A3 is equal to 0.52, and A4 is equal to 0.109. So these are the factors that people have derived for different phases of uh, cement and how much water they require for complete hydration. Okay, so if we assume OPC and its composition, suppose we assume as 48%, 25%, 13, 11%, and 9%, and we take into account these factors, so by multiplying these factors with these proportions, we can get the actual water that will be required for the cement system to undergo complete hydration. And by substituting this value, you will see value, it will come out to be 23 grams. So generally we say that we can say that for 100 grams OPC we require 23 grams of water for complete hydration. However, when we prepare concrete, we prepare generally with the high W by C ratio of say zero point 0.3 or zero point 0.4. Why is that so? Because we want initial workability in the system also, flowability in the system also. If we will take just 0.23 grams, 0.23 as W by C ratio, then my cement paste won't be workable enough to properly make it into a proper shape, or passes through a pipeline from concreting side to the molding area. Okay, so that's why you keep a little higher WYC ratio, which provides us the workability. However, in reality, the amount of water which is actually contributing to hydration will be only 23 grams per 100 grams of OPC. Okay, so this is the importance of chemically bound water. Now after water we have porosity. So porosity is something that will define the strength and the durability of concrete. So more porous is the concrete, weaker will be the concrete, and easier will be the ions from surrounding to go inside concrete and degrade the concrete. Okay, so porosity in cement paste, it is broadly classified into three types based on their size. Okay, there are gel pores which are extremely small, within 1 to 10 nanometer. Okay, and they are found within the gel structure of cement hydration. So we just now saw the CSH structure, the layered structure of CSH. So the pores which are present in between these layered CSH structure, these are known as gel pores. Okay, and they influence the shrinkage and the creep property. Then there are capillary pores which are present in the size range of 10 nanometer to few micrometers, and these are the water filled spaces in the paste that are not completely occupied by the hydration product. So when we talk about this Fedman Sereda model, this area which is water filled, okay, so upon evaporation or upon drying, when water dries off, there will be pores that will be created in these area, and those pores are known as capillary pores. Okay, so these are water filled pores initially that are not occupied by the hydration product. So these are those spaces. Okay, and then there is macro pores. So these are more than few mm. Okay, their size is more than few mm, and these pores, they result from incomplete compaction or entrapped air during mixing or placing of concrete. So suppose during concreting we didn't provide proper consolidation or vibration to concrete initially, so what will happen, there will be big pores that will be left inside the formwork or inside the mold due to improper compaction of low workability of concrete, and those big pores are known as the macro pores, and they are highly undesirable because they affect the integrity of the concrete or the paste system, and they will have a huge effect on the strength of the concrete also. So we try to avoid macro pores. Capillary pores is something that is governed by the density of our concrete or the densification of our pores, and gel pore is something that will be dictated by the amount of hydration products that are forming in the system. Okay, so this is how these pores are classified and how they are related to water or a cement paste assembly. Okay, so in this figure we can see where these pores lie in dimensional term compared to hydration product. So these are my interlaid particle spacing between CSH sheet, which is around 1 nanometer to 5 nanometer range. Okay, here is where my gel pores will also lie. Okay, now capillary pores are greater than gel pores, so they lie in the range of 10 nanometer to 1000 nanometer, or we can say 1 mm. Okay, so in this range we have capillary pores. There is aggregation of CSH particle which is around 1 mm, and there is the structure of CaOH haltoids and low sulfates which is around also around in this range only. And then when we talk about those entrapped air bubbles or air voids, they are ones which lie in a very macro size range of 10 to the power 3 nanometer, or we can say uh, it is around more than 1 mm. Okay, in that range. Okay, this is 1000 nanometers, so this is 0.001 mm, and this is more than 1 range. Okay, above 10 to the power 3 nanometer. Okay, so this is how these spores they lie on a dimensional scale. Okay, so like now we have an idea about porosity and water in a cement paste assembly. But if we know how much water we have added and how much cement we have added, how we estimate like what will be the porosity inside, or what will be the capillary water, or how much is the gel water, how we do that estimation. So for that, let's see one numerical. So this numerical, you would have seen the similar numerical in the course video also, where they talked about 100% hydration of the system. Now this is a little modified numerical where I have not completely hydrated the system, and I am asking you to calculate the gel porosity and capillary porosity. So just give it a try how you can go along with this question, and then we'll discuss the solution. And in the meantime, if you have any doubt regarding water and porosity, you can ask now. Just give this question a try. Just think about what steps we need to follow. So in this question, we need to estimate gel porosity and capillary porosity, which will be there in a mixture which is prepared by 100 grams of cement and 35 grams of water, and we need to assume that there is 75% hydration. Okay, it is not completely hydrated system, only 75% hydration is completed. And we know the density of hydrated cement, and we know that 28% volume of hydrated cement paste consists of gel pores. Any doubt in the discussion till now? Was my screen visible to everyone, or it got turned off? Can anyone reply? Hello, am I audible?
Yes, sir, audible.
So, were you able
But maybe,
to listen to the lecture till now, or did my network went off? Okay, just give it a try then. Give it a try to solve this question. And if anyone has any doubt in the porosity and water part of week 1 content, you can ask now. You can unmute and speak, or you can drop a message in the chat box regarding any of your doubt. So can anyone tell me like how you will approach this question? What will be the steps? Anyone has any idea? Pratik, my screen is visible. Just check once. Okay, it got turned off. Is it visible now? Okay, so just give it a try. This question that I was discussing before, So here we need to estimate the gel porosity and capillary porosity in a cement paste assembly prepared by 100 gram of water and 100 gram of cement and 75 gram of water, assuming 75% hydration. So can any one of you unmute and tell me like how you will approach this question? What are the steps that you need to follow? What is the base behind the question? So every one of you were able to hear the session till now, right? Like before the slide, whatever discussion that I did on porosity and water, or during that time also the screen went off. Can anyone tell me whether you were able to see those slides? Okay, can has anyone tried to do the calculation? Can anyone tell me the answer for gel porosity? How much they got? Okay, let's do it. Let me just tell you how to solve such questions. Okay, so what is given to us in the question? Mass of cement is given to us is 100 grams. Okay, and density of cement we know it is 3.15. Okay, mass of water is given to us 35 grams, and density is equal to 1. Okay, and we know degree of hydration is 75%. Okay, so when I talk about in unreacted state, okay, that is also known as anhydrous state. So total volume in anhydrous state will be volume of cement plus volume of water. Okay, so volume of cement will be nothing but mass upon density. So 100 upon 3.15 plus volume of water is 35 upon 1. So this will come out to be 66.74 ml. Okay, now we have given that there is 75% hydration. Okay, so for 75% hydration, if we assume that 23% water is required for complete hydration, okay, then we can say that volume of hydrated cement is equal to 1 plus 100 plus 100 into 23%. Okay, so this is the cement weight, this is the water weight. Okay, times degree of hydration, which is 0.75, divided by density of cement paste, that is given to us is 2.51. Okay, so this will come out to be 36.75 ml. Okay, so I hope everyone are clear with this equation. This is my mass of cement, and this is the amount of water required for 100 gram of cement for complete hydration, which is 0.23 times 100. And this is my degree of hydration. So in this, how much cement actually got reacted? It is 75%. Okay, so total ka 75% is required, okay, which is actually hydrated, and this is the density of my cement paste. Okay, so this will give me the volume of hydrated cement which is formed. Okay, now let me copy this. Okay, so we right now we know total volume in unhydrated and unreacted state, and we know the volume of hydrated cement paste. Okay, so next is we want to calculate gel porosity, and it is given that gel porosity is 28% of the volume of hydrated cement paste. Okay, so we can write volume of gel porosity Wg upon total volume, which is the volume of hydrated cement paste plus volume of gel porosity, is equal to 28%, or my factor 0.28. Okay, so solving this I will get the gel porosity which will come out to be 14.29 ml. Okay, so this is my total volume, this is the volume of my cement paste, and volume of my cement paste plus gel pores will give me the volume of hydrated cement paste assembly, the entire assembly. Okay, so 28% of this total volume is my gel porosity, so that's why I wrote Wg upon 36.75 plus Wg. Okay, that is 0.28. Okay, so this way we get the gel porosity as 14.29 ml. So this is the volume of my pores, gel pores. Okay, now we know volume of initial anhydrous cement, we know. Okay, we know volume of cement paste formed. Okay, now what is the volume of unreacted cement, okay, which has not reacted? So that is nothing but 100 into 1 minus 0.75, because 75 was the 75% was the degree of hydration. Okay, so the remaining 25 gram is something which has not reacted. So 100 minus 0.75 upon 3.51 will give me the volume of unreacted cement. Okay, 100 into 0.25 upon 3.51 will give me the volume of unreacted cement, which will come out to be 7.94 ml. Okay, so now we know volume of anhydrous cement, which was initial volume of the total system. We know the volume of cement paste finally which is formed, and we know the volume of unreacted cement. So what is the volume of capillary water? So we can say volume of capillary water is nothing but total initial volume minus volume of unhydrated cement minus volume of hydrated cement. Okay, so this will be nothing but 66.74 minus 7.94 minus 36.75. So it will come out to be 22.05 ml. Okay, so this is how we got the volume of capillary water, okay, which includes the water which is not reacted yet. Okay, any doubt in this calculation? Last topic when my screen went off, capillary pores. So just after capillary pores we got to this discussion of estimating gel pores and capillary porosity. Okay, so I was on this slide where we talked about gel porosity, we talked about capillary porosity, and I told about macropores. So macropores are those pores which are formed due to improper compaction or preparation of concrete, big voids that are created when compaction is not done properly, and this is something which affects the strength severely. Okay, then we came to this question. Okay, and this size range that I talked here, 1 to 10 nanometer, 10 nanometer to few micrometer, and greater than few micrometer, this the same thing I have attached one diagram here. So when I will share you this PPT, you can just go through this diagram. Okay, it is the same discussion that we did here. Any doubt in this numerical right now? How I calculated the gel porosity and capillary porosity? Was it clear to everyone? So similar question, I guess it was solved in the NPTEL session recording also, that the course recording, where where the professor talked about 100% hydration system. Okay, so similarly, when the system is not 100% hydrated, suppose in your exam, NPTEL exam, or anywhere it is given to us that degree of hydration is not 100%, it is 70% or 80%, and how to take into account that degree of hydration factor. Okay, so for that I framed this question where we have this additional 0.75 factor which is coming in the calculation. So you just need to remember how you proceed along with this question. You first need to find the initial volume of the system, which is the volume of water plus volume of cement. Then what is the volume of reacted cement paste, which will be depending upon the hydration degree. Okay, and then the volume of unreacted cement. Okay, these three calculation, once you do all these three calculation, you will get the gel porosity also, and you will get the capillary porosity also. Any doubt in this discussion? Just try to reply in the chat box or unmute and speak so that I am clear whether to move ahead or not. Anyone else have any doubt? If you have any doubt, you can unmute and speak also, so that in between the lecture, on the same slide on which you have doubt, you can ask. Okay, rather than waiting for me to stop my class and then see the chat box. Okay, so let's move ahead now. So this was all like the leftover part from the last week. Now for week 2 content, we'll first discuss about different testing methods for physical properties of cement. Okay, so in general, when we talk about properties of cement, okay, these properties, they are classified in two major categories: physical properties and chemical properties. So from the last session, we have seen the chemical properties, which relate the composition and hydration reactions that occur in the cement paste when it is mixed with water. Okay, so this includes different compounds that are formed on hydration, like CSH and CH, and what are the different clinker phases that are present in the cement. Okay, and presence of minor entities like magnesia, free lime, and alumina, those all things also. Okay, so those all things, they define the chemical properties of my cement. Now what is the end result? Okay, what dictates the use of cement in concrete? These questions are answered from the physical characteristics of cement. Okay, so different blends of cement used in construction are categorized by their physical properties. Okay, and these physical properties are critical in determining the suitability of a cement for specific application and ensuring that the desired performance is met in concrete. Okay, so when we talk about physical properties today, we'll discuss about normal consistency, specific gravity, soundness, fineness of cement, setting time, and compressive strength of cement paste. Okay, so these are the physical properties that we are focusing on today. Okay, so first is the normal consistency, or we can say standard consistency of cement. So we know that when we add water to cement, we form a cement paste system. Now, just after addition of water, the cement paste that we form, we say it is plastic in nature. By plastic, we mean that a material which has the ability to deform. Okay, so why plastic nature? Because suppose if we cover a cement paste, okay, this is my mold in which I have prepared the cement paste. Okay, Now if I remove this mold, what will happen? My cement paste, it will flow. Okay, and it won't hold its shape in which it was poured. This means that the paste deforms, and this is the property of plastic. It has the ability to deform. Okay, however, over time, as this paste will set and harden, it will lose its ability to flow, and this we say in technical term, it will lose its plasticity, or it will set. So we can say that workability or flowability of my cement paste is directly proportional to the plasticity. If higher is the plasticity, more will be the workability. Lower is the plasticity, lower is the workability. Okay. Now this degree of fluidity or stiffness or workability, any term you can take, that any term we can take for cement paste. Okay, this is known as consistency of cement paste. Okay, so what is the degree of fluidity or plasticity of a cement paste is known as the consistency of that cement. Okay, and what is normal consistency here? So it is the measure of water required to achieve a desired level of plasticity in cement paste. Okay, so initially my cement paste is completely plastic in nature. Over time, it loses its plasticity completely. Now, the amount of water required to achieve a certain level of plasticity, it is known as normal consistency. Okay, and what is this desired level or certain level? It is the amount of water required to make all air voids inside the cement paste isolated. So when we add cement in a bowl, okay, so these are small granules of cement. Okay, and these granules of cement, they will have some pores that are enclosed between them. So when we add water to this cement paste, what will happen? Slowly water will cover the each of the cement grain. Okay, so they say what is the desired level of water, the amount of water that is required to isolate this spore completely. Okay, suppose I add very small quantity of water. So what will happen? This spore right now, it is connecting all four cement grain. Okay, this is cement grain. Okay, as I will add more water, so what will happen? Slowly, this spore will get isolated from all the cement grains. Okay, so and it will look like this. Okay, now this pore, the air void between, it is not connected to any of the cement grain. Okay, so this some much water at which this occurs for the first time, it is the desired level of water that is needed. And amount of water to achieve this state is known as normal consistency of my cement. Okay, now, the normal consistency of cement, it is determined using by recording the penetration depth using Vica apparatus. Okay, and this testing is performed by following IS 4013 Part 4 guidelines. So, for each of the cement physical property testing of cement or concrete, there are standard guidelines that has been formed by Bureau of Indian Standard. Okay, so for normal standard consistency, we follow IS 4013 Part 4 guideline. Okay, now how we represent this normal consistency? It is represented in terms of the percentage water required to attain a certain level of plasticity. And in this testing, the plasticity is determined by recording the penetration depth. Okay, so code says for OPC, the penetration depth that we should get should be from 5 to 7 from the water. And to achieve this penetration depth, if my OPC is of good quality, the water content required should be in the range of 26 to 33% by mass of dry cement. Okay, so what this means that for achieving the penetration depth of 5 to 7 from the bottom, the amount of water that is required should be in this range. If it is not in this range, then we say that the cement that we have, it doesn't follow the standard guideline for quality. Okay, so now how we record this penetration depth? So we have Vika apparatus for this, that you can see in this picture here. Okay, so in this picture, there is this frame that you can see with the scale mounted on it. Okay, so and it is attached to a movable rod. Okay, so this rod, at the bottom of this rod, we attach a penetration plunger. Okay, okay. So what we do initially, we take cement and we add water to cement. We make a paste. Now, once we make this paste, we pour this paste in this Vika mold. okay, which has a diameter, upper diameter of 80 mm and height of 40 mm. Okay, once we pour the cement paste in this mold, we place it here on the platform, and we allow this plunger to freely penetrate inside the paste. Okay, once this plunger has penetrated inside the paste, it will attain a stable height, and then from the scale that is mounted on this on this rod, we measure the penetration depth. Okay, if that depth, suppose I added 30% water, if I got depth of 6 mm, then I will say that 30% is my standard consistency of cement. However, suppose I added 30% water and I got penetration depth of 10 mm from bottom. That means that I have not achieved the required penetration. So I will increase the water. Okay, I will increase from 30 to 32% or 33%, and I will repeat the experiment. If this penetration depth was supposed 2 mm, then it means that I have added too much water, because higher is the penetration, that this means that more is flowable is my space system. That's why the needle was easily penetrating. So what I will do, I will decrease the water content so that I can get into this range of 5 to 7 mm. So this is how on hit and trial basis we calculate the water content required for standard consistency. Any doubt in this testing of standard consistency? What is Vica apparatus? How we proceed along with the test, and what how we measure penetration, the iteration part. Any doubt in that? Okay, if there are no doubt, I'll proceed ahead. Okay, so that was standard consistency. Now, after consistency, the second up test that we have is specific gravity. Okay, so we know specific gravity of a cement is nothing but the ratio of density of cement to density of water at a specific temperature. And what specific gravities indicates? It indicates the quality and purity of a cement. Okay, as impurities like moisture and air void can affect the results of a specific gravity. And how we determine specific gravity? We determine by as per following IS 4013 Part 11 guideline using Le Chatelier's flask that you can see here. This is how a Le Chatelier flask look like. So how we determine specific gravity? We'll first pour this flask up till a certain volume indicator use with kerosene. Okay, and then we will add a known mass of cement to it, suppose 10 gram or 15 grams or anything. Okay, and once we add cement, what will happen? There will the volume in this flask, it will increase. So we'll measure the increase in volume. Okay, from suppose from 20 ml mark, it went up till 25 mm mark. Okay, so what will be my specific gravity? How it will be determined? Mass of cement that I have added upon volume of cement, volume of displaced, volume of cement displaced. So how much volume it displaced in this flask times the density of kerosene. Okay, which is a known thing to us. Okay, so from these three values we can get the specific gravity of my cement. And for OPC, generally the specific gravity is around 3.15. Okay, so this is based on Archimedes principle. Okay, when we add mass, cement mass, how much volume it displaced. Okay, so that displaced volume we are using along with the mass that we have added to calculate the specific gravity. Now there is one more alternative to calculation of specific gravity, that is using this specific gravity bottle, or which is also known as pycnometer. Okay, so in this we record five weights. Okay, we record the initial empty weight of pycnometer, suppose it is 70 grams. Okay, then we'll add cement up till a certain height. Suppose we added 50 grams of cement, so my total weight of water plus cement will be 120 gram. Okay, now I will add kerosene in this bottle up till this mark. Okay, so the total amount of kerosene that I've added along with cement, along with container, it will give me another weight. Suppose it comes out to be 250 gram. Okay, then I will remove the cement, I will remove the kerosene, and I will clean the beaker, and then I will completely pour this beaker with kerosene without cement. So I will get another weight which is suppose say 200 grams. So once I calculate all these four weights using this formula of specific gravity of cement, I can calculate the required specific gravity. Okay, and to know the specific gravity of kerosene, I will calculate one additional weight of container plus water. Okay, so that will help me to calculate the specific gravity of kerosene, which will come around 0.79 to point 0.8. Okay, so this is how we calculate the specific gravity using picnometer method. Okay, now based on this part of consistency in specific gravity, try to answer these three questions. And in the meantime, if you have any doubts, you can ask. I hope everyone are clear with specific gravity and standard consistency. Any doubt in these two concepts? If there are no doubts, you can answer the questions. What will be the answer for question number 2? The specific gravity of cement is found to be less than 3.15. Which of the following is the most probable reason? So, what can be the reason for OPC? My specific gravity should be 3.15. But suppose you got an OPC bag and you recorded specific gravity and it came out to be 2.9. Then, what can be the probable reason for lower specific gravity? Can anyone tell me which option is correct? Just think, like, it should not be like a right answer, but just give it a thought. What can be the reason? Can you tell me the reason why? Why fine grinding of cement will reduce the specific gravity? You can unmute and speak also. What is the reason? Anyone else wants to add on to this? Whether C is correct or any other option is correct? Can anyone tell me? Okay, correct answer for this is B. Presence of moisture or partial hydration. Okay, why? So if you remember the first question that we discussed today, I told you density, or we can say specific gravity of hydrated cement is equal to 2.51 and that of OPC is 3.15. So if there is some moisture or partial hydration in the cement paste, we know that specific gravity of that part, it will reduce. Okay, so if I get a cement bag and it has a specific gravity lower than 3.15, then we can say that it is due to hydration of cement, because specific gravity of water is 1. If it reacts with cement, it reduces the specific gravity of cement also. Okay, so that's why the correct answer is partial moisture hydration or presence of moisture. Okay, if there is higher proportion of iron oxide, then specific gravity will come out to be more than 3.15. Why? Because iron oxides come under the category of heavy metal oxides. Then fine grinding won't show any change in specific gravity because we use kerosene and not water. So specific gravity measurement, we are using kerosene and not water. And water is something which can react with cement, not kerosene. So fine grinding of cement won't affect the specific gravity. It is a material property. And higher lime content also may increase the specific gravity. Okay, there is only one reason which can decrease the specific gravity, that is the presence of moisture or partial hydration. I hope this is clear, Pratik. Okay. Try to answer question number 3. Cement requiring more than normal to achieve standard consistency may indicate. So remain cement requiring more water than normal level. Okay. To achieve standard consistency, what it will indicate if cement will require more water than needed. What can be the reason for a cement to require? Suppose normally an OPC bag requires 30% water to achieve standard consistency. Now I got a new OPC bag, but it is requiring 40% water to achieve standard consistency. Then what can be the reason for this? Why it is requiring more water? Can you tell me what will be the answer for question number 3? Anyone? Wow, yes, B is the correct answer. Can anyone tell me the reason why? What? Why finer grinding of cement will increase the water demand for consistency? Because no, it is not the high heat of it is the reason is the more surface area. So when we talk about finer cement grains, there is more surface area available for cement for reacting with water. So more is the surface area available for reacting with water, it will increase the demand of water to achieve a specific level of plasticity. Okay, plasticity is the flowability. Now, if surface area is more, reactivity is more. So, more water is consumed for the reaction part. So, I will require, in total, I will require more water to achieve a standard consistency also. Okay. Question number 4. Which of the following will reduce the measured specific gravity of cement? Okay, this is one reason that we saw. Now, this is again another question which is talking about what will reduce the specific gravity of cement with four different options now. So, can anyone tell me which is the correct option here? What will reduce the specific gravity of cement? Any guesses which option will be correct? Can anyone of you tell me why B or why C? How increase in alkali content will reduce the specific gravity of cement? And why adulteration with fly ash will reduce the specific gravity of cement? Okay, so the correct answer for this is C, adulteration with fly ash. Why? Because when we talk about fly ash, like later on during this lecture, in this lecture, we'll talk about supplementary cementitious material, and fly ash is one of the byproduct of industrial waste, and this is very light material. Okay, its specific gravity is generally around 2.29. So if my OPC includes fly ash, so what will happen in total? It will reduce the specific gravity of my OPC. Okay, so generally fly ash and OPC they are mixed together to form PPC, Portland pozzolanic cement. Okay, so this is what we use generally on site. Okay, because fly ash is a waste material and it needs to be consumed. And how it is consumed? By replacing a certain amount of OPC with fly ash, and it has supplement shows supplementary cementitious reaction. Okay, pozzolanic reactivity has the ability to show pozzolanic reaction. So slowly, as we will move along with this course, we'll understand fly ash better. Okay, so for now, remember that when we add something which has low density in cement, it will reduce the specific gravity of cement. So either it can be presence of moisture or partial hydration, or it can be adulteration with fly ash. Okay, now let's move ahead. So after consistency and specific gravity, the third property of cement that we will discuss is the soundness of cement. Okay, so soundness of cement is related to ability of cement to retain its volume upon hydration. Now, when we call a cement to be unsound, so cement is said to be unsound when it has unnecessary stresses, like expensive stresses that is building up in the cement paste, which can cause cracking. Now, how these stresses can build up in a cement, what is the reason behind, and what is the source that makes cement unsound? It is the presence of free lime or magnesia. So what happens if my cement has excess of CaO or MgO in its proportion? Then what will happen? CaO and MgO, they react with water and they form hydration product which are expansive in nature, which have high volume. Okay, now when we talk about a concrete, okay, in concrete we have very specific volume that is defined for aggregate, for cement paste, for water, and for air voids, a little volume for air voids. So if there will be certain product which is forming, which is expansive in nature, it will cause stress buildup inside the concrete, which can lead to cracking inside the concrete, and this is something which is not desired by us. Okay, so that's why we, it is important that in the cement, in the clinker that initially I have, there should be no free lime, excess of free lime of magnesia in that clinker. Okay, so if you remember in the first lecture, we talked about lime saturation factor to test the quality of cement. Okay, how we calculated lime saturation factor? Ratio of CO percent upon SiO2 plus Al2O3 plus Fe2O3. And we said that if this ratio is greater than 1, then we say that the cement contains, the clinker contains an acceptable proportion of free lime. Okay, which is not desired. Now, suppose we don't know the oxide composition of cement, then how we do the soundness check? So, for doing the soundness check of cement, we use Le Chatelier's apparatus that you can see here. Okay, so this is one mold, circular mold. These are two ribbons that are needles which are attached to this circular mold. Okay, this is a stone block and these are glass plates. Okay, and this testing we perform as per IS 4013 Part 3 guideline. 4031 part 3 guideline. So what we do, we initially we take cement, suppose 100 grams of cement we take, and we add water to cement. How much water we add? So code says you need to add 70% of water required for standard consistency. So suppose you did standard consistency testing and you got 30% water, in which you are achieving penetration of 5 to 7 mm. So 0.78 times 30% is the water that you require now for doing the soundness check of cement. Okay, so here you will require 0.78 times 30%. Okay, this is the amount of water you require here. So once we know the cement and we know the water weight, we prepare the paste and we fill the paste inside this mold. Okay, once we have filled the paste inside this mold and we have compacted the mold and we have leveled it from the top, we cover it with the glass plate at the bottom and at the top, and we place the stone on the top of the glass plate. Okay, and now this entire assembly of this apparatus along with plates and stone, we place it in a hot water bath, in a water. Okay, initially just water. Okay, so this is my bottom plate, this is my mold, this is my top plate and stone, and this is my needle, these needles which are there. I will completely immerse it in the water, and I will keep it in water, or we say immersed water bath for 24 hours. Okay, until my cement sets. Okay, now after 24 hour, what I will do, I will record the distance between these two needles. Okay, suppose it is coming out to be D1. Now I will replace this water with, I will boil this entire assembly at 100 degrees Celsius now for 1 hour. Okay, why I am boiling this system? So that I increase the kinetics of cement hydration that is happening here. Okay, in hardened state, if there is excess of lime, I will see volume expansion. Okay, so to check that, I am keeping it in hot water bath, which will increase the kinetics of the reaction. Okay, so if there is excessive expansion in the cement paste, what will happen? These two needle, they will move apart. Okay, because the paste assembly which is enclosed here, it will try to occupy more space which is not provided to the paste. So initially the needle was like this. Needle, it will become like this when there is expansion inside this mold. Okay, so after 1 hour of bath, I will again measure the distance between the two needle, and this time it is D2. Initially it was D1. Okay, so the difference between D2 and D1 I will record, and if that difference is less than 10 mm, then we will say that the cement is sound. If this difference is more than 10 mm, then I will say cement is unsound, and it has excess of free lime of magnesia in it. Okay. Everyone are clear with the soundness test? Any doubt in this? Any doubt in the soundness of cement testing? Why we are, how much water we are taking, how we are preparing the sample, why we are keeping it in immersion bath for 24 hours, why we are heating the entire assembly at 100 degrees Celsius for 1 hour. I hope everyone are clear with all the steps. Okay, so next after soundness is the setting time of cement, or we can say the most important property of cement. Okay, so we know from the discussion of consistency that workability is directly proportional to plasticity. Okay, so which defines the ability of a cement paste to deform. So we can say that setting of cement is related to loss of plasticity of cement or loss of workability of cement. Okay. Now, when we talk about cement paste or concrete, generally you would have seen that there are two setting times that are reported. One is initial setting time and one is final setting time. So what these two setting times means? So initial setting time is the time at which cement paste begins to lose its plasticity. So initially my cement paste is completely plastic, it is flowable. After a certain time, what will happen? It won't be completely plastic. Okay, so it will start to lose its plasticity. So the first moment when I see the loss in plasticity of cement paste, that time is known as initial setting time. And what is final setting time? So final setting time is when the cement paste has completely lost its plasticity. So if it is inside a mold and if I remove the mold, the cement paste will retain the shape, it won't flow. When this happens, we say that it has completely lost its plasticity. Okay, and that time to achieve this state is known as final setting time. Okay, so now can anyone tell me from what is the practical significance of this initial setting time and final setting time? Why both of them are needed? Okay, why not just define final setting time? What is the need of initial setting time also? So in practice, where is the use of these two time? Does anyone know? What is the significance of initial setting time and final setting time? Any guesses? Think about what is the practical need from concrete just after mixing. Yes, for transportation. Okay, so which factor is important for transportation? Initial setting time or final setting time? And what is the practical significance of final setting time? Workability management is also right. What about final setting time? on field, if I know the final setting time of concrete, how it will be helpful for me? Okay, so underwater construction for initiating curing. Curing is like, okay, once you prepare the concrete, duration of casting, okay. Any other point? You are close to the correct answer, but still not the perfect answer that I was looking for. Okay, let's talk about initial setting time. So initial setting time, we know it marks the first loss in plasticity. So we can say that beyond initial setting time, our concrete won't be freely flowable. Okay, it has lost certain amount of plasticity. So this means that if we are pumping concrete from a concreting part to the uh, plat, pouring area, so suppose this is my site where I am doing the mixing concreting preparation of concrete, and this is the site where I need to pour the concrete. Okay, so I am transporting concrete through pump. Okay, so this pumping, it should be done before initial setting time. Why? Because if I will do pumping after initial setting time, my pumping efficiency will be lower because concrete is not freely flowable. Or when I'm pouring concrete inside the formwork, since my concrete is not freely flowable, it may leave honeycombing or macro voids inside the formwork as it is not flowing properly. So this transportation of concrete and pouring of concrete, it needs to be done before initial setting time. Okay, and what about final setting time? So we know after final setting time, concrete loses all its plasticity and it is not flowable anymore. So this indicates that the foam works that we are using for concreting, if you know about foam work, on sites you have seen big wooden planks are used to give shape to columns or beams or slabs. Okay, so once I've poured concrete inside the formwork, if I know the final setting time, then I can know the time for removal of formwork. Okay, after what time I can remove the formwork and move to new locations. Okay, so this is the practical significance of final setting time. Now my cement is hardened enough that it is able to take its own shape, and now I can remove the formwork or I can transport the formwork to new site. Okay, so that's why it final setting time is important to us. Okay, and once we remove the formwork, we can start with the curing. Okay, by covering it with the jute bag or by spraying water. Okay, so these two points are very important from practical point of view, or maybe from exam point of view also. It is not just about how we do the testing, it is also important for us to know what is the practical significance of that value that we are getting. Okay. Now, how we determine setting time of cement in laboratory? So again, we'll be using the measuring the penetration depth using Wick apparatus, like how we did in the standard consistency. And this test of setting time of cement, it is performed as per IS 4031 Part 5 guideline. Okay, so we'll take cement and we'll take water. How much water will take? So code says you need to take 8.85 times the standard consistency. Suppose you are taking 100 grams of cement, and for standard consistency you got 30% water. So 0.85 times 30% water you need to take for setting time of cement. So taking this much water and this much cement will prepare the cement paste. Once we prepare the cement paste, we'll pour it in the Vika apparatus. Okay, in this apparatus mold, we will pour the cement paste. Okay, we'll tap it to remove air voids and we will level it from the top. Okay, once we have prepared this assembly, we'll place this assembly on this platform, and for initial setting time, we'll use this needle, okay, which has a surface area of 1 mm square. Okay, we'll attach this needle to this movable rod and we will penetrate the needle through my cement paste. Okay, and we'll record the penetration depth. Okay, now initially when you will penetrate this needle, it will penetrate till the bottom. So your penetration depth from bottom will be 0 mm. Okay, however, slowly as the cement paste will start to lose its plasticity, it will reduce the penetration depth also. So code says that the initial setting time is when it achieves when the penetration depth is 5 from the bottom. Okay, so suppose at 0 minute the penetration depth was 0 Okay, after half an hour penetration depth come out, after 10 minutes penetration depth is 1 Okay, so we'll take reading continuously after 5 minutes or 10 minutes until I get the penetration depth of 5 So once I reach the penetration depth of 5 I will see how much time has elapsed since addition of water, and that time is the initial setting time of my cement paste. And what about final setting time? So it will continue to take reading from using this needle. Okay, so slowly penetration depth will be 10 then 15 then 20 then slowly it will come out to be 40 Okay, so no penetration. This mold height is 40 Okay, so penetration is not happening, but it is leaving a mark on the top. Okay, so it is not penetrating inside but leaving a mark on the top. So when this happens, what we'll do, we'll change the needle with this needle, which has a small projection on the top. So the time when this needle leaves an impression and this needle doesn't leave any impression on the cement paste, that time is defined as the final setting time of cement. Okay, so code says that for OPC, my initial setting time should be greater than 30 minutes and my final setting time should be less than 600 minutes. If this criteria is not filled by OPC, then it means that the OPC bag that you are using, it is not following the standard quality. Okay, so this is about how we measure the setting time. Now, fineness of cement. So we know fineness of cement refers to the particle size of cement, and it is an important property that reflects the rate of hydration, strength development, and workability of cement. So finer is the cement, faster is the reaction with water. Why? Because finer is the cement, more is the surface area available of cement particle for reaction. And if more surface area is available, since cement hydration is a surface phenomena and hydration starts from surface, we can say faster is the cement hydration. Okay, so this is why fineness of cement is important, and we have discussed it multiple times now. Now, there are several methods that we can use to determine the fineness of cement, but the most popular method is using Blaine's air permeability testing. And this testing is performed using IS 4031 Part 2 guideline. So, what is this testing based on? So, this testing is based on the principle that finer cement particles allow less air to pass through them compared to coarser cement particles. Okay, so that's why it is known as air permeability testing. Okay, so how we perform this test? Okay, so in this test, we determine the time required for a known volume of air to pass through a compacted cement sample under a given pressure. Okay, so what we do initially, we'll weigh around 3 grams of cement. Okay, okay, and then we'll place that cement in this permeability cell. Okay, with filter paper at the bottom. Okay, and once we have placed the sample in this permeability cell, we won't do any compaction. We'll just pour the cement and we'll place one more filter paper at the top. Okay, once we have, okay, this is my filter paper at the bottom, this is my cement paste that I have poured, cement powder that I have poured, and I will place one more filter paper at the top. And then for compacting this system, I will use this plunger. So I will slowly insert this plunger from the top and apply a gentle pressure on the top so that I can form a compacted cement bed. Okay, now once my permeability cell with cement is ready, okay, I will place this assembly on this conical socket. Okay, so now once this assembly is placed and this plunger is all kept inserted on the cement paste, using this rubber bulb, I will introduce air in the I will raise the level of manometer fluid, that this fluid that is placed in this U tube. Okay, so I'll increase the level of this fluid up till this mark. Okay, using this rubber cork, I will create suction. I will increase the fluid level. Okay, once I have increased the fluid level, Okay, I will release this plunger and I will allow the air to pass, and I will record the time it takes for this fluid level to drop from this level to this mark. Okay, and the amount of time that the fluid takes to drop between two known points is what we use to define the spineless of cement, because the air which is passing, it is passing through this compacted cement bed. Okay, so if it is finer, it will allow air to pass slowly, so this drop will take more time. If it is coarser, the air will pass fast, so this drop will happen in lower time. Okay, so based on the time that we collect, we calculate the specific surface area of cement by multiplying it with the constant k factor, and this k factor we determine by using a material whose specific gravity we already know. Okay, so for OPC, specific gravity, specific surface area should come out to be greater than 225 meter square per kg as per IS 2269 guideline. Okay, so this is one of the very common method used for determining the fineness of cement. Any doubt in this? Any doubt in the setting time and the fineness of cement discussion? Okay, if there are no doubts, we'll move ahead to the next test, which is the compressive strength of cement. Okay, so what is compressive strength? It is used to determine the ability of cement to take compressive load. Okay, so when I prepare a cement block, how much load it will take before it fails. That load is known as the compressive load, and load upon area of surface area of cement will give me the compressive strength of cement. Okay, now to determine compressive strength of cement, we follow IS 4031 Part 6 guideline. So what it says that we need to prepare mortar sample, cement plus sand sample with the ratio of 1 is to 3 cement to sand ratio. Okay. Now, first question here I want to ask why we are not preparing just cement paste. Why we are moving into cement mortar here. The testing that we have seen till now, it uses cement paste. Then why here we are preparing mortar samples, not paste sample? Can anyone tell me the reason for this? Why for testing compressive strength of cement, we are not preparing cement paste, but we are preparing cement mortar. Mortar is cement plus water plus sand or fine aggregates. Why we are adding fine aggregate to the system? Does anyone know the reason? Because cement hydration is exothermic reaction. Okay, if I will just prepare cement paste block, it can undergo a lot of shrinkage cracking because of lot of exothermic reaction that is occurring between cement and due to reaction of cement and water. So to lower that hydration exothermic reaction, okay, we add sand to the system, which will provide the dimensional stability to cement, and it will prevent shrinkage of the cement block that can happen if there is no sand. Okay, so what code says, prepare mortar sample with 1 is to 3 cement to sand ratio. Then the size of mortar sample, code says it should be 70.6 mm cube, and the sand that I'm using is standard sand, quartz sand of three grades, grade 1, grade 2, and grade 3, each mixed in equal proportions. Okay, so grade 1 is sand particle which are greater than 1 mm size and lower than 2 mm size. Grade 2 is greater than 0.5 mm, lower than 1 mm, and grade 3 is greater than 0.09 mm and lower than 0.5 mm. So this is the finest one and this is the coarsest one, and all three are taken in equal proportion. Okay, so this is the standard sand we need to take, all three in equal proportion. Then for one cube, we'll take 200 grams cement and 600 grams of sand. And then this 600 gram, 200 gram for each grade we take. And we take a water amount of P by 4 plus 3%. Okay, I will mute you, Satyadeepa. Okay, so this P here is the standard consistency of cement. Okay, so standard consistency by 4 plus 3% of 800 grams water we take. Okay, so if you see this preparation stage, okay, there are three questions that I need to ask you here. Why we are using standard sand? Why these sand grades are taken in equal proportion? And why P by 4 plus 3%? Okay, P by 4 plus 3% of water is taken. Can anyone tell me the reason why standard guidelines fixed these three criterias for preparing cement mortar? Any idea why we are using standard sand? Why not any random sand we use for preparing cement mortar when we want to check the quality of cement? Okay, the reason is so that we can ensure that the quality of sand is not affecting the compressive strength value, and only cement is the factor which will affect the strength. That's why code says use a standard sand. Okay, so that the source of my sand doesn't affect the quality, the strength result. Okay, now why three grades? Because to keep a uniform grade distribution, and so that grading of sand doesn't affect the final result. The only change in the final result should come from the quality of cement and not from the quality of sand. Okay, that's why standard sand and equal proportion of three grades. Now P by 4 plus 3%. Why P by 4 plus 3%? So P by 4 because I have used 25% cement and 75% sand. So P by 4 is this represents the amount of water required by cement to achieve standard consistency. P is that water, and P by 4 is the total water for the proportion of cement I am taking, and 3% is 1% for each grade, water absorption for each grade, which is 1% for standard sand. Okay, so that's why P by 4 plus 3% of total 800 grams I am taking as total water required for preparing the mortar. Okay, so once I have prepared the mortar, I will pour it in cube. Okay, and then I will test the compressive strength of cube after 3 days, 7 days, and 28 days. Okay, so once I test the strength, I will record the ultimate failure load and I will divide it by the total cross section area, and that will give me the compressive strength. So code says that as per IS 269 for OPC 53 grade, on 3 days strength should come out to be this, on 7 days strength should come out to be this, and on 28 days strength should come out to be 33 MPa. If this is followed, then we say that the cement passes the criteria of compressive strength testing. Okay. Now, based on your understanding about fineness, initial setting, and compressive strength, try to answer these three questions quickly. So, first question says, if the fineness of cement is increased, what impact does it have on rate of hydration and heat generation? So, this is a very simple question. Can anyone tell me the answer quickly? We have discussed it quite number of times till now. What will be the correct answer for the question number 7? Yes, the correct answer will be C. As fineness of cement increases, the surface area available for reaction increases, so hydration rate increases and heat generation also increases. Now, question number 8. If the initial setting time of cement is below 30 minutes, what might be the probable reason? So we said that for OPC, the initial setting should be at least more than 30 minutes. If it is coming out to be less than 30 minutes, what can be the reason? Can you tell me the answer for question number 8? Why gypsum content? We talked that gypsum delays setting, not increase setting. The correct answer is C. Presence of highly reactive aluminates. So if you remember in the last session, we talked about C3, it causes flash setting of cement. Okay, so if there is excess of aluminates in the system, what will happen? Aluminates, it will react with water and it will cause flash setting, and that will reduce the initial setting time of my cement below 30 minutes. Okay. Now, question number 9. During the soundness test using Leach Atelier's apparatus, the expansion of cement was found to be 15%. What does it indicate? Okay, if my sound expansion is 15 mm, then what is the indication of quality of cement? Can anyone tell me the answer for question number 9? Yes, the correct answer is B. Okay, if my setting expansion is more 15 mm, we told that for a cement to be sound, the expansion should be less than 10 mm. If it is more than 15 mm, then it means that there is excess of free lime that is present in the cement system, and this cement system is likely to crack after setting because lime, when it reacts with water, it forms expansive products, okay, which is not desired for us in a hardened cement spaced system. Okay, so this was all about properties of cement. Okay, now we'll move into the next discussion about types of cement. Okay, so when we discuss about types of cement, we know till now we have talked about chemical composition and physical characteristics of cement. So from our understanding till now, we can say that simply by modifying the composition or physical properties of cement, the performance of cement can be changed favorably to obtain a different type of cement. Okay, so the first question that comes here in our mind is, why is this needed? Why we need different types of cement? Okay, so why we need different types of cement? So that we can have suitable binding material based on our project constraint, which are mainly location, application, and exposure related. Okay, so there are times when we are doing concreting in cold weather. Okay, so in such cold weather we want a cement uh, which is which has high heat of hydration, okay, so that it can react fast. Okay, where temperature is not supporting the reaction of cement. Or we have cement, we have in exposure environment which is in hot weather. So in such weather we want a binder which has a low heat of hydration, so that it doesn't show any shrinkage cracking upon hydration in such hot temperature. Okay, or there are cases when we have exposure of sewage line where sulfates are there is a lot of sulfate in the atmosphere, so we want a cement which is resistant to sulfate attack. So for different types of exposure environment or location, we may need different types of binding material. Okay, so that's why we study different types of cement. So today we'll discuss a few types of cement which are categorized in three categories. First is the ASTM classification of cement, type 1 to type 5. Then there is special cement like high alumina cement, super sulfated cement, white cement, and expansive cement. And then there is blended cement, which includes mineral admixtures like fly ash, slag, and silica fume. Okay, so what is the basis for all these cement? The basis is the composition of cement. So by varying the chemical composition, we can vary the reaction kinetics of the cement, and we can vary the suitability of cement for a specific requirement. And this variation in cement composition is dependent upon the proportion of raw meal that we are taking initially for preparing the clinker. Okay, so raw meal proportion that we are taking initially, it will vary the oxide composition of my clinker, and that oxide composition variation will vary the compound composition of my clinker. Okay, and we know each of these compound composition, they have different role. Like C3 is mainly required for high early strength, C2S is responsible for slow strength gain, C3 is responsible for reacting fast and causing flash setting, C4AF again is like C3 which reacts fast. Then alkali sulfates, they accelerate the early strength gain. Calcium sulfate, that is gypsum, it is used for as set retarders. And magnesium free lime, which are present, which they cause unsoundness problem. So we know each of this, the importance of this clinker phase. Okay, so just from the week one understanding, we can say that what composition will contribute how much to the strength. Okay, so can anyone tell me quickly, like which compound is represented by which curve? So you can see there are five curves here. Okay, each of this curve represents one of these phases: C3s, C2s, C3a, C4af, and gypsum. Okay, so and one among this is the entire cement. Okay, four these and one is cement. So which curve represent which phase? Can anyone tell me quickly? What will this curve 1 represent? Which compound is this curve 1 representing? Can anyone tell me? Whether it is C3s, C3a, C2s, C4af, which compound is this? Who is gaining maximum strength initially and slow strength later? Okay, this is C3s. Okay, we know C3s gains strength quickly. Okay, then curve 2, we can see it has slow strength gain initially and faster strength gain later on. So that is C2s. Then this curve 4 is something which doesn't gain any strength over time, very less contribution in strength. So that is C3a, and then C4af, which has the minimum contribution in strength. So these two have very low contribution in strength. So that's why their curve is not increasing. Okay, and this 3 is the cement, net cement, which lies between the four composition. Okay, now let's see about ASTM classification of cement. Okay, so ASTM, it classifies cement in five types of cement under this codal provision, ASTM C150, which is standard specification for Portland cement. And where these five type differ, they differ in the chemical composition and the intended application. Okay, so in the table we can see some minor and some major changes in the compound composition for each of the ASTM type. So type 1 is the conventional OPC, for which you can see the proportions are 49% C3s, 25% C2s, 12% C3s, 8% C4AF, and 2.9% calcium sulfate, which is gypsum. Okay, now in type 2, if you see compared to type 1, there is a major decrease in the C3A content. Okay, from 12% to 6%. So if there is less C3A, we can say that the threat for sulfate attack will be reduced. Why? So if you visit week one of the discussion, we told that if there is excess C3 in the system, initially C3 it reacts with gypsum to form ettringite, and if there is still C3 left in the system, this ettringite it reacts and it forms monosulfate. Okay. Now monosulfate in hardened state, when it comes in contact with sulfate ions, it again converts into ettringite. And this second reaction, it is expansive in nature. So if it is expansive in nature, okay, it can cause cracking in my concrete, which is not desirable. So if I will have less C3 in the system, so this second reaction it won't occur. This ettringite plus C3A won't form monosulfate. Okay, so that's why it will reduce the threat for sulfate reaction. So such cement is known as modified Portland cement. Now, in type 3, if you see compared to type 1, there is higher C3S content and lower C2S content. So, if C3S content is higher, we can say it will increase the rate of reaction of cement. Okay, so we can say this cement is rapid hardening cement, and that's why it is known as rapid hardening Portland cement, because it has higher C3S content. Then type 4, there is higher proportion of C2S and lower proportion of C3S. So this means that this cement will be slow strength gain cement, since C3S content is lower and C3A content is also lower. Okay, so it will gain strength slowly and it will set slowly. So that's why we say it is low heat cement, because if strength gain is fast, heat liberated will be higher. If strength gain is slow, heat liberation will be slow. So it is low heat Portland cement. Then there is type 5, where there is very low C3A content. And this type of cement is thus known as sulfate resisting cement, because it has very low C3A content. Okay, so this is how ASTM has proposed five types of cement from type 1 to type 5, while by varying the C3A, C2S, and C3A proportions in the cement composition. So if you see here, it shows the strength gain pattern of all these five types of cement. So this is rapid hardening cement, which is gaining strength quickly over time. This is my normal Portland cement. Okay, this is my modified Portland cement, which is very close to the normal Portland cement. This is slow strength gain cement, where there was high C2S content, and this is uh, super sulfate resisting cement, where also there was a little drop in C3S content. That's why strength gain is slower. Okay, so these are the five types of cement and how they gain strength over time. Now, similar to ASTM, Bureau of Indian Standard has also classified cement into major categories, and for each of these categories, there are standard codes that are defined. Like for OPC, we have three grades: 43, 33, 43, 53, for which we have three codes. Then there's Portland cement low heat, which has higher C2S content. Rapid hardening Portland cement, higher C3S content. Portland pozzolana cement, where cement OPC is blended with fly ash. Okay, there's Portland slag cement, where OPC is blended with ground granulated blast furnace slag. Okay, then there is sulfate resisting cement, which has low C3A content, and there is composite cement. Okay, so there are different classification of cement that are given in Indian standard also, just like American ASTM standard. Now, based on the discussion of ASTM classification, just try to answer these two questions quickly. So, question one is, you have been given the composition of cement. Now, based on this composition, can anyone tell me which type it belongs to? Okay, so I will just tell you what is the composition for type 1. So, this is the composition for type 1. Okay, based on this composition and based on this composition that you see right now in this question, can you tell me which type ASTM type cement it is? Can anyone tell me quickly what change they can see? What is increasing? What is decreasing? Okay, so this is type 4 cement. If you see closely, this cement has higher C2S content compared to type 1. If I increase the C2S content, it means that the my react cement is low heat Portland cement, which was type 4. Okay. Now, in question number 12, you have been given five types of cement and five application of cement. Okay, what each of the type is used for. So can anyone tell me for each of this option which ASTM type cement I should use? For cold weather concreting, where rapid strength gain is required, which cement type I should use? Can anyone tell me? Yes, rapid hardening cement. So that is ASTM type 3. Okay. Now for dam construction where I want minimum heat generation, which cement type I should use? So that will be low heat Portland cement as we discussed in the above question. Okay. So we need ASTM type 4. For aggressive environment, general construction in non-aggressive environment. If my environment is very normal, okay, for general construction purpose, which cement type I should use? Okay, so generally for area where the construction has no issue, there is no demand for high strength initially or low heat initially, I can go with standard cement, which is ASTM type 1. And for sewage area where it is exposed to high sulfate concentration, which cement type I should use? Okay, so for such area, I will require sulfate resisting cement. So that is ASTM type 5. Okay, so the correct answer will be option number A. Okay, so for each of this application, this is how different cement grades qualities are defined, and for each application, we can choose from different cement choices that we have. Okay, and this was about ASTM classification cement, which is very commonly used classification for understanding the role of cement composition and quality of cement and in application of cement. Okay, so after this basic classification of cement, let's talk about some of the very special purpose cement. Okay, so first among this is super sulfated cement. Okay, so this cement is composed of 80 to 85% blast furnace slag, 10 to 15% gypsum, and only 5% Portland clinker. Okay, so what is the property of the cement? It has extremely high resistance to sulfate. Okay, it has low heat of hydration and has lower strength gain compared to Portland cement. Okay, why this property? Because since there is very low OPC, okay, there is very low C3A phase in the cement, and thus it has high sulfate resistance property. Now, other two properties, low rate of hydration and low strength gain, because it has high proportion of slag. And you will see later on in next few classes that slag has low strength gain property over time. It requires OPC to release calcium hydroxide, and it reacts with that calcium hydroxide to form CSH. Okay, so it has slow strength gain over time. So that's why it has low heat of hydration and slower strength gain compared to normal Portland cement. And where is this super sulfated cement will be used? It will be used in environment which is aggressive to sulfate attacks, like sulfate rich soil or sewage work. However, it is not suitable for areas where rapid strength demand is required because it is low strength gain cement. Then similarly, there is high alumina cement, okay, which is produced by fusing bauxite, alumina ore, and limestone. Okay, and it contains calcium aluminates in very high proportion, and it is free from it. It doesn't have calcium silicates. Okay, it is mainly composed of calcium aluminates. Okay, so this cement has high early strength gain development. It has rapid heat generation during hydration, and it is still resistant to cement, still resistant to sulfate attack. Why? Because why are these properties there? Because calcium aluminate, it reacts readily with water, and thus it shows very high strength development initially. Okay, though we have talked earlier that C3A doesn't contribute to strength development, here we are talking about calcium aluminate and it is not C3A. Okay, these are other phases of calcium aluminates which can react with water to form calcium aluminate hydrates, which can show strength development. So that's why, since calcium aluminates are highly reactive, it shows high strength gain over time. And why it is sulfate resistant? Even though we have calcium aluminates, because it is not C3A, it is other phases of calcium aluminates. So when we talk about high alumina cement, it has calcium aluminate or C12A7. these are the phases of calcium aluminates that are present in the cement, and these phases does not are not aggressive to sulfate exposure. Okay, when they hydrate with water, they form stable phases which are not aggressive to sulfate attack. Okay, that's why they are resistant to sulfate. And where is the cement used? For repair purposes, where I require rapid strength early, or for refractory purposes for heat resistance. Like in furnaces, if I want to do repair, I use this high alumina cement, or in aggressive chemical environment, high alumina cement is used. Then there is white cement, which is composed of limestone, kaolin, and sand. Okay, this is brilliant white in color and moderate strength, and it is used for decorative purpose. There is expansive cement, where Portland cement is added with calcium sulfates and aluminates. Okay, and where they are used, where I want to fill the cracks. Okay, so there I want something which will react with water and expand so that it can fill the crack. So there we use expansive cement. So you can see, just by modifying the properties of cement, we can have cement for very special purpose applications also, like super sulfated cement for sulfate rich condition, high alumina cement for high early strength properties, white cement for decorative purpose, expansive cement for crack filling. Okay, so these are some of the very common special purpose cement. Okay, try to answer these two questions based on the understanding of special purpose cement. What will be the answer for question number 30? You can ask doubts also in between if you have any. How the white color comes to white cement? Okay, so this is due to the composition of cement. It is contains highly pure limestone, and limestone is white in color. Okay, so if you see lime, when it is used for as a binding material, it reacts with water, and it forms calcium hydroxide and calcium carbonate. Calcium hydroxide and calcium carbonate both are white. Calcium carbonate is a white precipitate, so that's why it is known as white cement, because it contains highly pure lime. There is very less quantity of iron oxide in which, and we know iron oxide is the reason why we get that color of cement, grayish texture of cement. Okay, so that's why high purity limestone is the reason. Try to answer this question. Question number 13. What is the main hydration product in supersulfated cement that contributes to resistance to sulfate attack? This is not supersulfated. This is high alumina cement. So, which hydration product in high alumina cement contributes to sulfate attack resistance? Can anyone tell me? Can anyone tell me the answer for question number 13? So it is the calcium alumina hydrate. So we have talked just now that in high alumina cement, though there is high alumina content, it is still resistant to sulfate attack. Why? Because there is no C3A phase that is present in the high alumina cement, which converts into ettringite to monosulfate, and then monosulfate reacts with sulfate. Here in high alumina cement, when it reacts with water, it forms calcium aluminate hydrates, and these aluminate hydrates are not reactive to sulfates. Okay, so that's why we say that it is this phase that makes the high alumina cement resistant to sulfate attack. Question number 14. A concrete structure requires resistance to both high temperature and sulfate. So, which cement I should use if I want to resist both high temperature and sulfate? Can anyone tell me the answer? Yes, the correct option is high alumina cement, as we have seen just now. Okay, it has good sulfate resistance also, and it has high strength gain initially, and it is suitable for high temperature application. It has good heat resistance properties also. Okay, so if you will see in repair of furnaces, in internally we apply aluminate high this alumina cement for layering of furnaces because of this property of the cement. Okay, now the last topic after ESTM classification and special purpose cement, we have blended cement. So we won't talk much about blended cement right now, because later on when we'll talk about mineral admixture, those mineral admixtures are again what we take in blended cement. So blended cement is something where we substitute OPC with an alternate material which can show cementitious behavior. And these alternate materials that we talk, these are known as supplementary cementitious material. And these supplementary cementitious material will talk when we'll talk about mineral admixtures. Okay, so right now I will just touch up upon what is blended cement. In detail, we'll talk in mineral admixture section. So, from where this concept came of supplementary cementitious material? From ancient practices, particularly when volcanic ash and hydraulic lime was used for construction. So, we know hydraulic lime, when it is mixed with water, it forms certain hydration phases which shows strength. Okay, so non-hydraulic lime, okay, it reacts with CO2 to form CaCO3. Okay. However, hydraulic lime, it reacts directly with water itself to form hydration products which can show strength. So this concept of hydraulic lime, it paved the way for SCMs in modern time. Okay, because why it is showing reaction with water hydraulic lime? Because it has impurities of clay, and these impurities are rich in silica and alumina. Similarly, volcanic ash, which Romans discovered when lime is mixed with volcanic ash, it since volcanic ash is rich in silica and alumina, it reacts with lime to form calcium silica hydrates and calcium aluminate hydrates, which again show strength development over time. So these two were ancient practices of supplementary cementitious materials which paved the way for modern cementitious material. Okay, so these volcanic ash and hydraulic lime in ancient construction directly inspired the development of modern SCMs, and the key principle was reactivity, durability, and environmental efficiency. So volcanic ash act as a pozzolon. It reacts with calcium hydroxide produced during the hydration of cementitious material, and this resembles the modern SCMs like fly ash and silica fume. And hydraulic lime has the ability to set under water due to its silicate and aluminate content. Okay, and this resembles the modern SCMs like granulated blast furnace slag, which shows both pozzolanic and hydraulic property. Okay, so this is how we came to modern SCMs. Okay, so we can say that the Romans, they unknowingly practiced sustainable construction by reducing lime required, just as SCM reduces clinker consumption in modern time. Okay, and this paved the way for modern SCMs. Okay, so in modern SCMs, what are there? There is presence of clay which are rich in aluminosilicates. Okay, in fly ash, which is a byproduct of thermal plant, it is produced by pulverizing coal, and it has mineral impurities like clay. And these mineral impurities is why fly ash is reactive with OPC. Okay, so what happens? This clay has aluminosilicates. OPC, when it reacts with water, it produces calcium hydroxide. So these aluminum silicates, it reacts with calcium hydroxide to form hydration product, and that's why fly ash is used as a supplementary cementitious material. Similarly, slag, it is a byproduct of iron and steel industry, and it is produced by quenching molten slag. So that slag has mixture of silica and alumina, which are impurities. Again, this silica and alumina rich impurities, it can react with calcium hydroxide produced by OPC to form hydration product. Similarly, we have silica fume, which is a byproduct of another alloy industry, and it also contains very high silica content, which makes it reactive towards calcium hydroxide produced by OPC. So we can see that all these three materials, which are very important SCMs in modern time, they are they all are byproduct of some other industry. They are all waste, but due to their reactive composition of alumina and silica, they are used as an substitute for OPC. So what we do, we reduce a certain amount of OPC and we replace them with these SCMs. So the waste that OPC is producing, which is calcium hydroxide, SCMs, they utilize this calcium hydroxide to form hydration product, and this forms the basis of modern construction practices. The use of SCMs in modern construction practices. So earlier we saw this description of Portland pozzolana cement and Portland slag cement. So these two are one of the examples of these SCMs. So in Portland pozzolana cement, we replace 25 to 35% OPC with fly ash, while in Portland slag cement, we replace 30 to 40% OPC with down granulated blast furnace slag, and they pave the way to blended cement application. Okay. So this is how the composition looks like. Pure OPC has high percentage of CaO, while these SCMs, they have higher proportions of silica and alumina. So in fly ash and GGBFS, you will see higher proportions of silica and alumina, while in silica fume, you will see very high proportion of silica. And due to this high proportion of silica and aluminates, they are able to show supplementary cementitious reaction. Okay. Any doubt in this part of blended cement? Okay. So this was for today. We discussed about water and porosity. We talked about testing of cement, where we talked about soundness, consistency, setting time, compressive strength, and specific gravity. And then we talked about different types of cement: ASTM grade 1 to grade 5, special purpose cement, and blended cement. For blended cement, I didn't went in deep discussion because there will be a complete lecture on mineral admixtures where we'll again talk about blended cement and their reactivity. So today I just touched you upon what blended cement means and how, from where they originated. Okay.